Hi, this is going to be the last video where we will be talking about the Cartesian plane or how we describe the built and natural environment using a flat surface. First, I'm just going to clean up a little bit my drawing here, and then I'll start explaining this video's new concepts. So let's delete these two, the compass, the protractor that I placed there. I thought I was going to use it, but I didn't use it. I'm just going to delete indicate these angles over here. Just gonna get rid of them. Just gonna delete this bit here as well. What else can I just keep? I'm just going to delete this part. And also I am deleting, let's see what else. Yeah, just going to delete all these formulas. We're not going to need them for the following calculations anymore. I'm going to keep this. We're going to delete this one and get rid of this and these annotations as well. And I'll leave the horizontal angle at P3. So yeah, so let's keep going here. What I'm going to do it is that I'm going to display the values for all the internal angles, and we'll take it from there. Let's also just color the axis so they are all in the same color. I'm going to delete these things here. We know this continues towards infinity. No need for that piece of information anymore. And yeah, I'm just going to get rid of this one and this one here. Just the numbers are going to color them the same way as well. Just a little bit of cleanup. Okay, I'm just gonna stop the video and then I'll just show the end result of what we are going to start working on from where we start working today. Okay, I just finished up cleaning a little bit. Let's call it my board. Okay, so you can see everything what's going on here. Now, on the previous video, we ended up just talking about the internal angles. So I'm gonna explain a little bit more what the story is with the with internal angles in a closed polygon. So in a closed polygon, you have these internal angles which are colored in red, and you also have external angles that are here colored in blue. These values that are colored in green, they are actually horizontal internal angles, okay? You need to be careful how you use the instrument on the field, because depending on what you do, you are going to obtain the internal or the external angles. So what's the relationship between an internal and external angle? Well, if you take this internal angle, say at P3, you take that value from 360 degrees, then you're going to obtain the blue one, the external angles. Just gonna do this for one point only. So I'm just gonna grab this one here, this value, this horizontal angle there, which I know is internal because this value is smaller than 180, okay? So anyway, I'm just going to calculate the external angle at point P3. So I just type in 360 degrees because that's the entire circle, minus 76 degrees, 7 minutes, 34.67 seconds. And that value that I have there, it's my external angle at point P3. Okay, just gonna type it in. It's a 283. So I have here 283. 52 minutes and 25.23 33 seconds. 25 33 25.33. Is that correct? Let me just check. That is correct. But now I'm going to color that value in blue. Okay, just to make a difference between a visual difference between the internal angle and the external angle. Now, how are all the internal angles or external angles related in a closed polygon? We have a way of a theoretical model that is free of error, hence the reason its name a theoretical model, where it says that if I sum all the internal angles inside a closed polygon, I just need to input here the amount of internal angles I have in that closed polygon, and then apply the formula, and that's going to give me the sum of the internal angles in a closed polygon. So I have a quadrilateral here. I know that I have 1, 2, 3, and 4 angles. So I just look for my calculator here, and then I apply the formula, this one. Okay, so I have 4 internal angles minus 2. I have that result, which is 2. And then I multiply that by 180 degrees. And that is my model, my theoretical value, the perfect value, okay? That this is the mathematically correct value. But then I need to double check that's true. How will I double check that? Well, I need to add all these internal angles that I have here, and they should be this same value, okay? Now, if when you are on the field and using an instrument, you're going to have some errors in your observations. Okay, basically errors are divided into gross errors, which is mostly related to bad use of the instrument. You just have no clue what you're doing. Then you have systematic errors that they can be compensated, but most of the time that is due to instruments that are not calibrated. Okay, so how you mitigate a systematic error? Well, you send your instrument for calibration. And then you have the other error, which is random error. And we cannot eliminate those. We can reduce them by developing better methodologies of getting data, or uh, or using instruments that are more accurate. Okay, but it doesn't matter what you do, that random error will always be there. There's no way of eliminating it completely. Okay. So after you have carried out all your field observations, you are going to turn that into internal angles as a result. And then when you add them up, that practical value that you are going to get on the field will never match the result of the application of these theoretical models. But that's not the problem there. That's actually okay, because then what you're going to do, it is that you're going to compare your theoretical model with your practical value, and the result of that computation is going to be called your angular error. I'm going to stop here because that's not the goal of this module. That's why you have to go to the land surveying module, so they'll explain more about that. But this is, just to give you a little bit of context. Um, so if you apply the second model here, which is for the external angles, let's just see what is the sum of the total of all those 4 internal angles together. We just go and use our theoretical model. So this is the value that we are expecting. How many external angles I have? I have 4 plus 2. I have that value. And then I multiply that by 180. And that is the sum of all the external angles. Now, notice that when you are carrying out surveys, you have to either observe the internal angle or observe the external angle. So you'll get more information in that regard in the relevant modules. Now, There is another angle that is very important, mostly for, just going to delete this, which is important for road surveys mostly, okay? And it's called the deflection angle. So what is a deflection angle? So imagine, just going to delete these circles here. So imagine the following. What happens if you are standing at P1, but you do not change your line of sight between P4 and P1? So you are P4, you walk all the way to P1. Now you're standing at P1, but you are not changing your line of sight. So you're going to have something like this. Sorry, it's the other way around. You know what? Just gonna do it this way. Okay. This is the deflection angle that I'm talking about. This angle over there. And that is called a deflection angle. Now, these angles are really important when you are designing roads because depending on that angle, you're going to design a curve, a bend, okay? And the length of that bend, or let's say how strong the bend is, how close it is, will be dictated by the value of a deflection angle. You can calculate this angle of deflection by using orientations. Why? Because you have the orientation of the from P4 to P1, but again, you're not changing your line of sight. And then you have the bearing, whole circle bearing, between from P1 to P3. So if you subtract those two orientations, then you're going to get the angle of deflection. Let's just carry out a quick calculation with that one. So I'm talking that I'm standing at P1, but I'm still looking at the same direction. I haven't changed it, okay? So I was in P4, I walked all the way towards P1, and I'm still looking in the same direction. I'm not looking anywhere else, okay? So that is the equivalent of me doing the following in the calculator. So I have my previous direction, which is from P4 to P1. So I have the one from P1 to P4. That's not a problem. I know that if I take my that orientation from P1 to P4, which is 180, 58 degrees, 57 minutes, and 44.96 seconds. That is from P1 to P4, but I need the back bearing from P4 to P1. I just add 180 degrees. The demonstration of why it's 180 degrees difference is shown on the previous video. So this is my direction, okay, from P4 to P1. But remember, I walked all the way from P4 to P1 and I haven't changed my line of sight. I'm still looking at the same direction, okay? Then I take my direction or the orientation from P1 to P3 to this value that I have here in my calculator. So I have, again, I have the whole circle bearing from P3 to P1. So I just add 180 degrees to this value, and then I obtain the back bearing, or the bearing from P1 to P3. So minus 292 degrees, 37 minutes, 11.51 seconds. And that is going to be my angle of deflection, this one that I'm indicating here. Okay. So those are the main angles we deal with in land surveying: internal, external, and deflection angles. Okay, what else can I calculate on my Cartesian plane once I have the coordinates here? So I have my rectangular coordinates. We can describe the same points using the polar coordinate system as well. Um, with the rectangular coordinates, I am able to calculate orientations, and then with orientations, I can calculate internal angles. With orientation, I can also calculate angles of deflection. Once I have the internal angle, I can calculate the external angle, and I can also calculate uh, horizontal distances. Okay, but now, what else can we calculate here in this closed polygon? I can calculate the area formed by those four vertices there using my Cartesian coordinates. Okay, why do we do this? Say, for example, that you have a plot of land that has this configuration and you want to sell it. How will you know what the area is? Or because you need to know the area in order to establish a price. Okay, so prices of land is given by hectare or square meters. Okay, but we need to know first how the extents of our plot of land. Now, back in the day, where satellites um, surveying with satellites or using other surveying methodologies, legal mapping, which is a branch where you just survey boundaries of lands and then you register, you make them legal. Then you create a piece of document that says that that land is yours. Before we had coordinate systems, I'm talking like probably like 100 years ago, surveyors were still able to establish the boundaries of a property, but what they mostly used was that they measure all the distances between significant points. This before could have been, I don't know, an oak tree. P1 was a column for the entrance of somebody else's house. P3 was a corner close to a river, because that was the way boundaries were defined before. So they would tell you, for example, from these three located at P4, um, there is a distance of 49.117 something else, because back then they didn't use meters, they used different units of length, and they used a bearing as a way of describing the boundaries. So those documents, the map added to those legal documents, they would look something like this. They place the distance there, and then they would also indicate the orientation of that line. Okay, so anybody else would have been able to recognize these features in real life. So if somebody wanted to check the location of this plot of land in space, well, they just had to find, say, the mango tree or the oak tree or any tree there, and then they would use the compass and then walk on the direction as surveyed by the surveyor back then, and then a measure of distance. So each one of these four sides would have had an angle and an orientation and a distance. Okay, so how are we going to calculate the area? As initial inputs, just going to delete a few bits here. Let's see, what can I use? What else can I use here? I'm just gonna delete this value. Going to delete these ones there. I'm just gonna leave those there. So as an input to calculate the area, we're going to use the rectangular coordinates. Okay, and we are going to organize them in this manner. So I'm just gonna copy them here. All right. Actually, I'm just gonna copy the. Let's see if I can copy just this. There you go. So I can copy that. Okay, I'm gonna generate a copy of my rectangular coordinates. So I copy my table there, and then I need to organize the coordinates. Okay, so I need to organize the coordinates in a clockwise direction. Okay, in a clockwise direction. So I just need to pick an initial point. Let's see which one. All right, I'm just going to start from P2. And if we are going clockwise, then the following point is P4. So what I'm going to do here, it is that I'm just going to move these cells a little bit, to this area. And then the next vertex that I'm just going to put there, it's P4, then it's P2. So I just go here to P2, just reorganizing my coordinates. So the method that I'll explain works. Okay. So I need to organize my coordinates in a clockwise or my table in a clockwise manner. So first is P1, then P4, then P2, and then P3. So after I have organized my table following a clockwise order, I'm going to duplicate the first two vertices and I'm going to place them at the bottom of my table, just the way it looks right now. Then I proceed to calculate the following. Okay, so I'm just going to proceed as follows. Just going to move this table over there to give myself a little bit more space. And this is the way it works. Okay, I'm just going to put the formula here. The first calculation is going to be the result of the following. So I'm going to take the coordinate x of P2. So P2 x coordinate minus the x coordinate of P1. And this result, okay, let me just use a different grouping sign symbol. Okay, just going to use that. And this group will be multiplied times the y coordinate of P4. Okay, I'm not going to demonstrate where this comes from. You just need to apply it. How do you calculate an area using this method? Well, first you generate a table, then you organize the points in a clockwise manner, and then you duplicate the first points and the first 2 points and place them at the very end of the table. Okay, this works for any internal or closed polygon of any amount of vertices. Okay, so it is pretty much, just to mark it here, it is pretty much the coordinate of P2 minus the coordinate x of P1, and then that result is multiplied by the y coordinate of P4. Okay, and then you have the formula there. Now we have to keep going here and repeat the same methodology. So in this case, we are going to work with the following. We take these coordinates there. So the following one is going to be the coordinate x of P3 minus the coordinate x of P4, and that result is going to be multiplied by the coordinate y of P2. Okay, we're going to do the same. Okay, which is now where we'll be operating here between these these numbers here as I'm indicating. So then is the x coordinate of P1 minus the x coordinate of P2 multiplied by the y coordinate of P3. And lastly, because if I have 4 coordinates, I need to have 4 computations. I work with this last pair as I'm just indicating here. Okay, so it's going to be the coordinate x of 0.4 minus the coordinate x of P3 times the coordinate y of P1. Okay, these might look like very difficult, but what I suggest you it is to focus on the pattern and then just apply the methodology, and that's it. Then once all these calculations are done, you're going to add up all of those values and divide by 2. And the resulting value is going to be your area. Okay. So this is, you add up all those values, and then this result needs to be divided by 2. Okay. So let's just apply that. Okay. Using my fancy calculator here. Okay. Now, before I start using my fancy calculator, I'm just going to plug the values indicated in these equations here so it makes sense. All right. Once I plug all the values in these equations, then we will carry out the calculation. So I'm just going to generate a copy of all these. Sorry, just hold on for a second there. Let me see. This is okay, cool. All right. So I'm just going to copy these values here, this over there. Now there's a little bit of overlap. So I'm just going to move this to the side just to make a little bit more space. Okay. Now these x coordinate for P2, it is minus 25. Okay, so this is minus 25. And then the coordinate in x for P1 is 10. Okay, I'm just going to put these values in brackets so we understand what the story is with the signs as we carry out the calculations. So then I'm going to place the value for this here, y coordinate for P4, which is minus 22.5, minus 22.5. Okay, and I'm going to also just put this bracket here just to make sure that we don't forget about the signs of the magnitudes that we are placing here. Now then we have a coordinate x of P3, which is minus 20. So this one is here minus 20. And then the coordinate x of P4, which is 22.5. 22.5, and then times the coordinate y for P2, which is minus 10. So minus 10. And let's just click on here. This is coordinate x for 1. So this is 10. And then the coordinate x for P2, which is minus 25. Minus 25. And then a coordinate y for P3, which is 22.5. Then the coordinate x for P4, which is 22.5. And the coordinate x for P3, minus 20. And then P1y, So the y value for P1, which is 10. Okay. Now I'm going to carry out all those calculations and I'm going to place the result just beside this and just have to move this again. Let me see, just there. Okay, now I bring my fancy calculator and then I'm going to have that minus 25. I can, just write the equation, the numbers right, the same way they are here, just to avoid any confusion. So I'm just going to do that. So bracket, minus 25, close, minus 10, close this bracket, times minus 22.5. And that's my result, 787.5. Just gonna move this number there, this here. Okay. Just gonna place that here. And my result is since 787.5. 787.5. Okay, just gonna move this value a little bit just to make it different. Or, just not different, but, we don't get confused. Now I'm going to calculate the following line. So bracket, minus 20, close bracket, minus 22.5, close bracket, and close bracket, times minus 10 equals 425. All righty. So just put that value there, 425. Now we'll keep calculating things here. So bracket, 10, close my bracket, minus, open bracket, minus 25, close bracket, times 22.5, 22.5. They are the same. Okay, yeah, 7. So I'm just gonna place that value over here. And then finally, I have bracket, 22.5, close bracket, minus, open bracket, minus 20, close, times 10. And then I have 425 again. Then I add up all that results, all those numbers. And then I have 787.5 plus 425 plus 787.5 plus 425. This is my result, 2425. And then this result I divide by 2, and that is going to be my area. So back to my calculator, divided by 2, 12.5. So 12.5 square meters. And that's the result I was looking for. This is the area enclosed by this closed polygon. And I have the rectangular coordinates of each vertex. So yeah, so that's it for this video. So any questions you can ask me during the tutorial hours. Talk to you soon.